Welcome to T3 Day 9 of Calculus. Today we're going to continue our discussion of the fundamental theorem of calculus. The key thing to remember is this statement right here, that statement right there, and the verbalization as well, which states that the integral of a velocity function is equal to the net change in the position function. So if you have the position function for a velocity function, you can just use those two values to find the actual net change in the position function, which is the area under the curve from A to B of the velocity function. The new word is this word antiderivative, where capital F will represent the antiderivative of lowercase f. The key thing is that the derivative of capital F is equal to lowercase f. That's the same relation as this. The derivative of the position function is the velocity function. So let's do an example. We are given this velocity function right here. Nice and fun, and has sign in it. Awesome. And it gives the velocity in feet per second of a person, where the positive velocity means going north. So positive means going north, which is pretty common. Also suppose that at time equals 0, the person is 5 feet from his home. That's important. Write an integral expression that represents his position at time equals 4 seconds. So that's going, and then evaluate it. So that's going to be the initial position, like where the person starts, initial position, and then plus the net change. That's the net change in position. So what is the initial position? Well, we write it as the s of 0, that's the position at time 0, plus, and the net change is the integral from 0 to 4, in this case, of v of t dt. So we know that this right here is 5 because of that statement right there. Now we need to find this net change, which is right here. This is the net change right there. Now this function right here is a little complicated, and we don't know how to find the antiderivative yet by hand, so we're going to use a calculator. So what you end up with is 5, the initial position, plus, and then when you run this integral, you end up with negative 49.821. So the final numeric answer to this is going to be negative 44.821. And what is this? This is the position of the person at time equals 4. Position of person at time equals 4. So in practical terms, it means 44.821 feet south. Feet south, because positive is north. So now we're going to write an integral expression that represents his position at 8 seconds, and we can evaluate it. So that's going to be very similar. S of 0 plus the integral from 0 to 8 of v of t dt. We can evaluate that, and then end up with negative 24.414 feet. So what about at time equals 12? Well, it's very similar. S of 0 plus, again, 0 to 12 this time, v of t dt equals. Now, just as a reminder for those of you that don't have integrals written like this on your calculator, I'm currently typing in fn int y1, the function, our velocity function I have typed in as y1 x, 0, 12, and I'm adding 5 to that value. And I've done it a few times, so all I'm doing is hitting second entry, and then changing just the numbers that I need to change. So 12 plus 5, and I hit enter. And this time I ended up with negative 32.773 feet. And now it's asking to write an integral expression that represents the total distance, total distance. Remember, total distance is absolute value the person traveled in the 12 seconds. So the integral expression is going to be the we don't need the initial position, because this is just distance, total distance traveled. Distance traveled is irregardless of where the person started, so as long as the velocity function stays the same. So in this case, we're doing the integral of 0 to 12, but this time it's the velocity in absolute value. When I type this into my calculator, for those of you that don't have the nice clear type, I think that's what it's called on your calculator, I typed it in as fn int, and then it goes abs for absolute value y1, comma x, comma 0, comma 12. And when I hit enter on that, it can take a little while because the absolute valuation of a function takes a little while. It comes out to be 78.586 feet. And if you need to remember to find absolute value, that's math and then num, and it's the first option to get absolute value, symbols like that. In this case, it was the ABS. It might show up that way. So in this case, we are given a velocity function and we are given the associated position function. We're going to evaluate each of the following without a calculator. So the way we do this is we need to figure this one out. As the fundamental theorem of calculus tells us, we need to evaluate the position function at 4 and subtract it with the position function at 2. Well, we've been given the position function, so we plug those values in. And when I plug it in, I mean you're plugging in 4 into the position function. So it's 4 times 4 cubed minus 2 times 4 squared plus 3 times 4 minus 1. And you are subtracting from it the same thing when you plug in, oh, is that negative 2? Sorry, it's negative 2 right there. You're plugging in negative 2, so 4 times negative 2 cubed minus 2 times negative 2 squared plus 3 times negative 2 minus 1. This math isn't particularly challenging, but you can make mistakes really easily if you don't plug this into your calculator properly. Okay, so what about this one? What's the only thing that changes? Well, the velocity function is the same here, so we're going to use the same position function as given to us up here. We're going to end up with s of 2 minus s of 0. I'm not going to do these out. You can do them out on your own. So let's jump to 4, where we get this nice graph here. So this is the function f of x, lowercase f of x, lowercase f of x. So which is greater, f of 2.5 or f of 5, lowercase f? So that's just plugging in 2.5 and 5 into the function. So 2.5 is right about, I would say, let's say 5 is right there, so 2.5 is right about, I don't know, here. There's f of, and we can label it to the left here. It's more accurate to say like this. So that right there is f of 2.5. What about f of 5? Well, this seems to be, f of 5 seems to be 0. So which one's bigger? Well, f of 2.5 is higher. What about capital F of 2.5? Capital F of 2.5. So how do we figure that out? How do we figure that out? Well, so how do we figure out what capital F looks like or what the values are if we don't have it and we just have this picture? Well, the fundamental theorem of calculus tells us the integral from 0 to t of f of lowercase f of t dt is equal to capital F of t minus capital F of 0. So let's say we plugged in 2.5 for t. So 0 to 2.5 of f of the integral of f of t, oh, I gotta write dt. If you plug in 2.5 is going to equal capital F of 2.5 minus f of 0. So what does that tell you? Let's just add f of 0 to both sides. So you end up with the integral from 0 to 2.5 of f of t dt plus, sorry, excuse me, plus capital F of 0 equals f of 2.5. Now we could do something very similar to f of 5, and we would get the integral from 0 to 5 of f of t dt plus f of 0, it's 5 in this case, is equal to f of 5. So the f of 0 is in both of them. So what we're doing here is, if those are the same, how do we compare the sizes? Well, we look at the integral from 0 to 2.5 and we look at the integral from 0 to 5. Which is bigger? The area under the curve from 0 to 2.5. What's bigger? This area right here, or if you keep on going to 5. What's bigger, half of it or the whole thing? Well, the whole thing. The whole thing is going to be bigger. So f of 5 is bigger. F of 5 is bigger. What about f of 5 or f of 10 here? So f of 5 is this whole area. Well, f of 10 is that whole area minus this one because it's below the x-axis. So which one's going to be bigger? Well, f of 5 is going to be bigger because f of 10 takes away, to get f of 10, you have to take away all of this down here. Okay, so what about 10 or 15? Well, 15 is the same as 10, except it's adding in this amount. It's adding in that amount. So which one's going to be bigger? F of 15 is going to be bigger. So then what about these differences? Well, this right here, that is the same as the integral of f lowercase f from 2.5 to 5 of lowercase f of t dt. So that's the area under the curve from 2.5 to 5, or the area under the curve from 5 to 10 of f of t dt. Which one's bigger? The area under the curve from, this one is from 2.5 to 5. What's bigger? This area right here, or 5 to 10? This area right here. Well, one of them is positive and one of them is negative. The yellow is positive and the blue is negative. So which one's going to be bigger? This one's going to be bigger. the last question is, for what x value will f of x, capital F of x, attain the maximum value? So what's going on is that capital F of x starts at a certain value here at 0. We don't know what it is, but as t gets bigger going this way, what happens at first? Well, at first, f is gaining value right here. Gains a lot of value, like that, and then it subtracts that value. So it's going up all the way to 5, and then it's going down, and then it's going up again like this. The question is, when is capital F of x maximized? Well, it's big right there, and then it gets smaller, so it's going up and then down right there. And then it's going down, down, down. It's going down from here to here, and then right at 10, it starts going up again. It starts going up again, and then it keeps on going up all the way to 15. The question now is the overall area bigger there or there? And you can answer that by comparing these two spaces here. Which is bigger, the blue or the yellow inside that blue oval right there? Well, what happens is it gets to a max height here and then goes down a bunch, but doesn't recover all the way. It doesn't recover all the way, so it's going to happen at x equals 5. And I've been conflating x and t in this, so sorry about that. But I just mean, when I say t, I mean the horizontal variable. So it's at 5 because it goes down a whole bunch and never recovers, even though it goes up a little bit.